Okay, so we're going to go through the notes for sections 3E and 3F. So sections 3E and 3F are going to be describing Newton's third law. So we already went through the second law. We're now looking at the third law. And the third law is more conceptual. It's going to let us describe how forces act on objects. So right here is the actual text of the law. This is the way that it's normally phrased. It says that whenever one object exerts a force on a second object, the second object is going to exert an equal and opposite force on the first object. So this is a good example right below here. So you have one object A, you have another object B. What's happening is they're touching each other and they're exerting a force on each other. So again, you're getting two separate, distinct forces. So again, those forces by Newton's third law is basically says when objects interact, when they exert a force on each other, you're going to have an equal force, but it's going to actually be opposite in direction. So we can see that here. One force is going what looks like to the right. The other force, it looks like it's going more to the left. So we call these, we have a little bit of vocabulary for these forces. We're going to call that first force the action force. So the first force that we look at. And then the force that responds to it is going to be called the reaction force. So again, let me draw another quick example. So let's say you had a wall, then you threw a ball at it. Ball hits the wall. So again, what you'd have is you can have, when they interact, when they exert a force on each other, you're going to have one force exerted on the wall. Let's call that the force applied 1. And then you're going to have another force that the wall exerts on the ball. So you're going to have another force in the opposite direction. Let's call it FA2. And these forces, you can see them, they're opposite in direction. They go opposite directions. But they're going to be equal. They're going to be the same size. So again, that's really what Newton's law says. It kind of describes this interaction and how big these forces are and which ways they go. So very important to keep in mind with this. Remember that the forces, and I already said it, but just a reminder, keep in mind about the action and reaction forces, they're equal in magnitude. So again, these two forces up here, FA2 and FA1, they're going to be the same size, basically. They would have the same value. They're going to be opposite in direction. So, right, you can see this FA1 is to the right, FA2 is to the left right here. And they're going to be acting on different objects. So let's look at these two forces right here, the ball and the wall. So FA2 is acting on the ball, and it has, let's just give it a sample value. Let's say it has 10 newtons. So by Newton's third law, the other force, right, that's acting on the wall is going to have the same size. It'll both have 10 newtons. But the difference here is that they're going to be in opposite directions. Where we see the force on the ball up here is going to be to the left. The force on the wall is actually going to be to the right. And keep in mind they're acting on different objects. FA2, the force applied 2, is acting on the ball, and the force applied 1 is actually acting on the wall. This kind of summarizes how, this interaction, the forces share some stuff in common, but there's a couple differences when stuff interacts. Now we're going to move on to the next part of the note, so the second page, the 3F part. Nope, that's not it. Here we go. So the 3F. So this is going to describe a little bit more in detail Newton's third law. So it said before, in the previous section, if two objects are exerting a force on each other, and there's no outside forces, that force is actually going to be the same. So if they're isolated from all their forces, the force on each object will be the same, but the acceleration might be different. So again, we can have the same force on two objects, but you might actually have a different acceleration. So there's a couple reasons why that might happen. Why? So these are really explaining why this happened, why you might have an acceleration that's different. So one reason is the objects could have two different masses. So if the objects have two different masses, you're going to have two different accelerations, because by Newton's second law, the object with the larger mass is going to have a smaller acceleration. So again, let's say we had two objects, object 2 and object 1, and there was a force on each one of them. So if there's a force on each one of them, by Newton's third law, that force is going to be equal, but what's not so obvious is that if the mass, let's say mass 2 has a really large mass, it's going to have a really small or comparatively small acceleration. While the first object 1 might have a smaller mass, it's actually going to have a larger acceleration. So again, what could happen is they could have the same force on each other, but because the masses are different, you're going to have a different acceleration. Another reason why you might have a difference or why you might have the same force, but you might not actually have the same acceleration on both objects, is there could be other forces in play. For example, if you have I don't know, like a baseball hitting a car, sure, baseball, car, and they're running into each other, and you get, two forces coming out. Right, if the car has other forces being applied to it, it's going to be a whole, it's going to have a different acceleration than would be predicted by Newton's third law. Because once there's other forces, like there's the force of friction, and there's the force of gravity, and there's the normal force, this is going to get a lot more complicated, and we're going to need something a little bit more than Newton's third law to look at it. So this is going to make a little bit more sense with an example, but the overall is that if you have two forces, or if you have two objects, they might have the same force on each other, and that's what's predicted by Newton's third law, but you might actually have a different acceleration. And again, that could be the results of the objects having different masses, or it could be a result that there's actually other forces in play that you didn't initially think about. So in the remaining time, let's see a quick example about the second law, or the third law, sorry. So here we are. I'm going to give you an example. So again, before you see the solution, make sure you attempt it. So please, attempting the problem before you go through. Okay, so now I'll show you the solution for this problem. We have a blue car with a known mass. It runs into a parked red truck, 5,000 kilograms. The red truck experiences a force of 1,000 newtons on it. What is the force and acceleration of the blue car? So we're going to neglect friction, so we don't have to take friction into account. So the first thing is we want the force on the blue car. So Newton's third law basically says that all forces, if you have an interaction between two objects, those forces are going to be equal. Because there's no friction, so there's nothing else we have to take into account. If there's just that interaction, the two cars, the two forces, those forces are going to be equal. So we're going to have the force, I'll draw it quickly. So we're going to have the force on the car, and then we're going to have the force on the truck. And we're going to call the force on the car FA2. We're going to call the force on the truck FA1. So again, those forces are going to be equal. They're going to have the same size by Newton's third law. So the force on the car is going to be the same as the force on the truck. And remember, there's no friction, so there's nothing to throw a wrench in this to make it more complicated. So again, they're going to be equal, and we know what that value is. We know it's 1,000 newtons. It's given in the problem. We know those two forces are going to be equal. The next thing is we need the acceleration on the blue car, or of the blue car. So if we remember, the net force is equal to the mass times the acceleration. There's really only one force on that blue car, and that's really the applied force 2. It's going to equal to that mass of that blue car times its acceleration. We actually know what that force on the blue car is. We just found it. So we know it's 1,000 newtons. We know the mass. So we know this. We know the mass. We know the mass to be 1,200. It states it in the problem. And from this is quick division, and we'll get out the acceleration is 0.833 repeating meters per second squared. So that would be the acceleration. Okay, so that's the problem. Again, that was Newton's third law, the notes for it. Make sure your notes are annotated. Make sure you have this example problem written down. And that's it for now.